All right. So we are back to it at the end of one more week, which means we've got 2 more weeks left, right? 6 classes with you guys, right? Oh man, we're running out of time. So, got just a couple of classes left for you guys. You guys are done with the lab, though, right? Is that, or I think some of you guys are lab. No, everyone's done with lab now, right? Yeah, you guys are. So we're wrapping it up very quickly here. So we're going to pull into chapter 11 today. But that's only part of it. Basically, section 11.2, if I remember correctly. Let me double check. Yeah, section 11.2. That's the only part of chapter 11 that I'm ever going to teach you guys. Dr. Tong might go through some more things and whatever, but that's the intermolecular forces are the most important thing. One of the most important things that we can discuss in general chemistry. It's going to be extremely important in an upcoming class.
OChem?
It's an OChem also. So, well, I keep saying this, and I think I mentioned it to you guys before, but chemistry very much builds upon itself. It's not really until you get to like your senior year and like biochem and things like that where you look back and like, oh yeah, I learned that in gen chem. Oh yeah, I learned that in organic or wherever it might be. So it does kind of build up on itself, and so I'm just trying to give you guys the vision of the future there, so to speak. But that's what we'll do today, and it shouldn't take too long to get through. We'll just have to kind of describe some of the basic principles of the intermolecular forces, but my understanding is you guys already know everything there is to know about the intermolecular forces because you guys had lab about it, right? And what did you guys do? You guys did like dissolving things? Is that what it is to like dissolves like? And you guys talked about polarity and all this kind of stuff?
We went through like dissolves like. We never got an explanation as to why the heck it wasn't following that rule.
What do you mean?
Like the like dissolves like thing did not actually happen.
Yeah. Because it's as most things in chemistry, what we do is lie to you guys so that you guys miss points on the sand, right? So we say things like octet rules and then we violate them all the time. And we say things like dissolves like, and then that doesn't work at all, right?
There's no explanation.
No, there absolutely is an explanation. I'll talk to you guys a little bit about it. But so anyway, where we had ended up though is we had just finished talking about polar bonds, right? We talked about electronegativity and how that affects the polarity of bonds, whether we have non-polar bonds or we have polar covalent bonds, right? And it's all this kind of relative assessment of the difference in electronegativities, right? And once we had figured out where our polar bonds are, we had taken that into our geometries and looked for overall dipoles, right? Is a molecule pulling in one direction overall, right? We talked a little bit about the vector addition and all this kind of stuff with that, right? Very important questions. You guys can expect to see that on the exams that's coming up, right? So hopefully you guys remember that what you have to do is draw your Lewis structure, then your molecular geometry, then you find your polar bonds, and then you see which end is winning the tug of war, right? That's the rules for how you describe polarity, okay? And that same idea is what's going to lead us into our intermolecular forces, okay? So intermolecular forces are kind of tacked on to the end of figuring out whether a molecule is polar or not, okay? So we're kind of building off of the tail end of this, and it fits into where we're talking about in the current chapter itself. That's why I pull it into this section here, is what it is. Okay, so done rambling for a bit. Let's start again with prayer, and then we'll pick it up from there. But Lord, we just thank you yet again, just for another just a wonderful blessing of this day, Lord, and just another opportunity to seek you out. And just to learn a little bit more about your creation and your world and the things that you've put around us, Lord. Lord, just we just stand in awe in front of the things that you have made, Lord, and just help us to recall that it is you who have created these things, and just help us to understand a little bit more about you today, Lord, in whatever way that might be. We just pray that we can take a step closer to you in our faith today, and we just pray that you ignite that flame in our hearts, Lord, just to continue to seek after you passionately. And just pray all these things in your name. Amen. So, I don't really have any slides about this stuff for you guys because it's kind of all visual anyway. But I will be giving you guys a couple of things to think about here, or kind of things to write down. And the first important thing is that we're going to be discussing 3 intermolecular charges, or excuse me, intermolecular forces, right? The book talks about 4. I'll tell you why I only care about 3 of them, and I'll make that distinction, okay? So there's 3 intermolecular forces. Now, those intermolecular forces don't all exist in every molecule, okay? Except for the first one that we'll talk about. And so we'll just I'll kind of explain the different parts where it comes in here. But let me give you the overall picture. Intermolecular forces are the forces that are inter the moleculars. You guys got that?
Amazing.
I know. It's shocking, isn't it? Now here's the thing. I-N-T-E-R, intermolecular forces are how molecules talk to each other, right? So just like you guys have multiple ways of communicating with each other, email and text and Facebook, right? There's different ways that these molecules can talk to each other. Some are direct and some are indirect, if you want to think about it in that way also, right? Now, we also have to consider there are things called intramolecular forces. And intramolecular forces of how a molecule talks to itself, how the atoms within a molecule talks to each other, okay? And we'll talk a little bit about that as we end this up here and as we move into the next section, okay? But anyway, if you're going through a video online or you're reading something out of the book and you hear them talk about intramolecular forces, that's different, sort of, from intermolecular forces, okay? So for our intermolecular forces, we got our 3. The first one is our dispersion forces, right? So we got dispersion forces. Try this one more time. There it is. Okay. Now dispersion forces, we also call van der Waals forces or London dispersion forces. Right? So I'm going to make a very clear statement to everybody, okay? Dispersion forces are the least strongest form of interaction until they aren't.
Thank you for that clarification.
You're welcome. You guys got it? They're the least strongest form of communicating. They have the least energy of interaction until they don't. Now, what in the world does that mean? Well, let me back up for just a second. Every form of intermolecular interaction is based off of one thing. Can you guys guess what that might be? Electrons. Shocking. I know, right? To think that electrons do chemistry and affect the properties of molecules.
Absolutely.
Okay? So it's all based off of electrons. So let's do a little mind exercise here. Let's say I've got nitrogen. Okay? Elemental nitrogen, N2. Hopefully at this point you guys could draw the Lewis structure for that. You guys could talk about the formal charges. You guys could talk about how many bonds there are, all this kind of stuff, the geometry, right? So real quick, how many total electrons are there in N2? Not just valence electrons, how many total electrons are there?
30? No, sorry, 14.
14, right? So each nitrogen has 7, so we add all those together, right? Now, I'm not talking about just valence electrons, and we'll get to the distinction here in just a little bit, right? We just have 14 electrons. Not too bad, right? Let's say that all of a sudden, we move all the way to iodine, I2, okay? Another diatomic molecule, right? The Lewis structure, at least, doesn't look all that different from N2. Of course, there are single bonds and triple bonds, this kind, right? But it's just 2 atoms stuck together. How many total electrons are there in I2?
106.
A lot, right? You guys with me on this? So what if I'm telling you that the intermolecular force is all based off of how many electrons there are? Wouldn't it make sense that iodine, I2, has a stronger method of communicating with another molecule than nitrogen does? That seems to make sense. You've got 10 times the electrons, to keep the math simple. You guys following along with this? Yeah, what's up?
Would the size of the electrons, right now, the molecule or atom element change that too?
Yes, absolutely. Yeah, we'll talk about that. Okay, yeah, what's up?
For dispersion forces, you said that they involve the least amount of energy. Is
Until
that
they don't.
also true? Okay.
Until they don't, yeah. And well, I'll make it very distinct here for us in just a second. I'm just trying to get you guys to, I disagree a little bit with the book and how they describe it.
Okay.
And I'm just trying to clarify this a little bit.
That's good.
Okay, so now N2 is a gas, right? You guys are taking a deep breath, right? You know, the majority of what you guys breathe in is nitrogen. It's a gas, right? What does that mean about how one nitrogen molecule talks to another nitrogen molecule?
Stably.
What do you mean?
If it's that common, then it must be a pretty stable molecule.
Ah, okay, so hang on to that. That's you're talking about why nitrogen exists. And you're right with that. That's actually a very interesting thought. But I'm talking about why does nitrogen exist as a gas, right? What did we learn way back in chapter 1 about gases? How much do they talk to each other?
Not that much.
They don't at all, right? So what does that tell us now about the intermolecular forces? Well, if they don't talk to each other a lot, they've got to have very weak intermolecular forces. You guys following me on this one? Right? They don't talk to each other, they just zip around on their own and do their own thing. Okay? Now what do we know about iodine? I2. It exists as a
Halogen.
solid at room temperature, right? These beautiful purple crystals that you guys can isolate, right? You can isolate them yourself from seaweed if you even wanted to. Kind of a cool little experiment that you can look up on YouTube there, right? Although be careful what you search. We'll talk about that later when it's not recorded, but different reasons here, okay? But iodine, right, exists as a solid. What does a solid tell you about how these molecules are talking to each other? Well, remember in a solid, these molecules are very close to each other, right? They're stacked on top of each other. Does it mean they have good communication skills?
Yeah.
Right, yeah, they're communicating with each other very well. Okay? Now the only thing that iodine and N2 have in common is that the only intermolecular force they have is dispersion. Got it? So there's got to be something else going on here, right? Dispersion, right, hang on just a second, right? Iodine has a much stronger intermolecular interactions through its dispersion forces than nitrogen does. And it's all related to how many electrons there are. That's what it comes down to. The more electrons, the stronger your dispersion force is, okay? So that's what I mean by it's the weakest until it's not. If you get to large molecules, like your DNA has a massive, massive, massive dispersion force that goes with it, okay? Because there's millions of electrons involved with it, all right? I'm not saying it's necessarily the most important in DNA, I'm just saying it's got a huge, right? It's got a huge amount of dispersion forces in there, okay? So the point I want to say is that dispersion exists in every molecule that we talk about. And it's a direct function of how many electrons there are. Okay, the more electrons, the stronger it can talk. The stronger things can talk to each other, right? The stronger they can stick together, okay? And that's going to affect some of our properties, which we'll talk about a little bit later. What's up?
So, does the fact that when iodine is a solid, does the fact that it's like a crystal mean anything? Like, or is that just like?
I mean, a lot of pure elements crystallize in their solid form.
I know, but
What do you mean though? Does it? I just want to say what are you saying because of the forces therefore it crystallizes or?
no, I'm just asking like, well maybe. Like, does the fact that it takes like a crystal shape, like its molecules take that like, sort of, geometric structure, does that mean anything? Or?
Yes. So the way that solids pack together, they do it in a way to minimize void spaces, right? So if you think about the ball pit at McDonald's, right? And so if you have a pit and you throw a bunch of balls in there, right? They all settle down to minimize how much space there is in between them, right? It's the same way with atoms. If you just think of atoms like spheres, right? They're going to settle in a way so that they maximize their interaction while minimizing how much empty space there is.
So that's just general, not specific.
Correct.
Okay.
Right now, your question might come, you're asking a very complex question, actually. Because your question is this the only way it's gonna exist? Why does it take that structure of a crystal and all these kind of things? And those are all great questions, but we can't really explain it just based off of this principle. What we can explain it with is that the why things pack together in a certain way in a crystal is because of these interactions. That's a good way to start that explanation.
What the heck's up with carbon then?
What do you mean?
Well, I mean, carbon, you've got like your graphite, that's like slidey
Yeah.
planes. You've got your diamond, which is just like, and what are the other forms of carbon? Okay, I'm not awake yet, but I know that like carbon in its pure elemental state
Yeah.
has like a ton of
4.
different.
It has 4.
Okay, that's still a lot.
It is, absolutely.
Like configurations.
Correct. So what we're talking about there is allotropes, is what those are called. Different naturally occurring forms of an element, right? Oxygen is an example of that too. O2 exists, and so does ozone, O3, right? So these are just called allotropes. Now, your question again is the same as what Michael was asking. Why do these things exist? Well, there's different thermodynamic and kinetic reasons for those, right?
You gotta get
Diamonds will slowly over millions of years turn into graphite, right? So there's a
Seriously?
right. So there's a different set of ideas that go along with that, and we'll learn about that in Gen Chem 2. Okay, so we'll talk about that there. Anyway, so let's think a little bit about what a dispersion force is. Now, one part that I'm disappointed with your textbook is they were this close to greatness, right? They were this close to greatness. Because what they say is that dispersion forces, the non-scientific term that they use is squashiness.
I'm sorry, what?
Squishiness, so close to greatness. So close to greatness, right? And that's what it is, right? So when we're talking about this, the scientific term for squishiness is polarizability, okay? So now that we kind of understand what's going on with a dispersion force, it's based off of electrons, how in the world does it work? That's the next question, okay? Well, it's based off of electrons. Where do electrons exist?
The shells, orbitals?
In orbitals. And the orbitals are around the individual atoms, right? So let's think here for just a second. Here we have our buddy nitrogen, right? Or well, actually, we'll just do it with iodine, okay? So there's our simplified Lewis structure for iodine. Where are the electrons in iodine? Are they existing exactly in between those two iodine molecules in a nice straight line the way we draw it?
No,
No,
they have hybrid.
right? They're existing in what we consider an electron cloud, okay, that surround the two atoms. Got it? Remember, we have the lone pairs around there, we have the bonding pairs in there. They're existing in these orbitals, and those orbitals surround the atoms themselves. Got it? So there's a cloud of electrons that's floating around these iodines. So let's say this iodine atom is floating around in space, okay? And all of a sudden,
Oh, no.
it starts to float next to this iodine atom over there. You guys with me on this? Right, so we have these two iodine atoms that are coming close together. What's gonna happen?
Bounce off each other?
Maybe. They're gonna get closer to each other, yes.
Attach?
Would they snap
Maybe.
together?
Hmm?
I would think that they would snap together. 'cause
They could, you're absolutely right. Yeah, they could do some kind of reaction where we make bonds. You're absolutely right. What's the first thing that each of these individual iodine atoms are going to encounter though?
Electron.
The electrons. You guys with me on this? There's this cloud of electrons floating around. Can I come pick on you for a second?
Yeah.
Do you want to come up here and be famous for the 10 people who are going to watch this? Okay? So imagine, I'm sorry, you sit in the front row, right? You know, you get picked on sometimes, right? So imagine, it's like this, right? So imagine that Andy and I are the iodine atoms here, right? And we've got our electron clouds around us. I'm going to get a little bit closer to him. I'm going to get a little bit closer to him. And he slowly gets very uncomfortable, right?
Yeah.
Right, thank you so much, I appreciate that, right? That's.
No,
Just
yeah,
that.
he called you up just.
I'm sorry, I gotta pick on a guy, because, you know, well, otherwise a professor, and, all right. Yeah. Anyway, so what happens is the two electrons or clouds are gonna get closer to each other. And as soon as they do, what's gonna happen?
Something,
Something negative is getting closer to something negative, and what happens?
repulsion.
He got very uncomfortable. So what are those electrons gonna do? I'm gonna go to the other side here, right? That's exactly what happens. The clouds come together, they start to repel each other, and one of the sets of electrons get pushed to the other side of the molecule. You guys with me on this?
Mhm.
So it looks like this, right?
If
So-
the electrons get pushed over, does that make that side more positive?
Perfect, right? So let's say that we move this closer together here, right? And those electron clouds are the things that start to run into each other. So let me redraw this here for visual sake, right? So what happens then, right? The electrons are going to hang around that other side of the molecule a little bit more. So what does that mean?
It's become polarized,
Well, and what does it mean to become polarized?
to have a partial negative and partial
We
positive.
have negative and positive ends. Not full negatives and not full positives, but partial negatives and partial positives. Yeah,
So is that what a dipole is? Like what it would be?
yes, yeah, I'll condense this down into a nice sentence for you guys in a second, right? But this is exactly what's happening. As you bring things closer together, the electron clouds interact, the electrons are gonna repel, and you leave partial positives and negatives, right?
So is this thing going to be less intense with nitrogen?
Yes, because you have less of an electron cloud, right? So now we see in green that we temporarily have negatives and positives. You guys with me? What's attracted to positives?
Negatives?
Negatives. Negatives from where?
The
Well,
other.
from the blue cloud here. So what's gonna happen on the blue cloud? The electrons are gonna say, hey, there's something positive. What are they gonna do? They're all gonna move to one side of the molecule. Got it? So what happens at the blue ion then? Well, on the blue cloud here, right? When they see that, they're going to rush to that end over there, right? And then that becomes negative, and that becomes positive. And then what's gonna happen?
Another one.
Another could come, right? You guys with me on this? You guys see how this starts to happen then?
Yep.
The bigger that cloud, the more stuff can slosh around. The more stuff can slosh around, the more positive and negatives we can create. Okay?
Is this just because they encountered each other? Like,
Yeah, that's part of it, right? This can happen, so to speak, spontaneously, but if you try to imagine electrons just suddenly existing on one side more than the other, I kind
I'm
of.
saying like the atoms, they're not attracted to each other before they repel those electrons. Like what brings them together is just. in the
They're
first place, it's
they're
like
moving around, right?
Okay.
This is, I have to be careful with my term here. This is a good thing, right? Negatives and positives coming together release energy, right? So this isn't like there's something bad going on, it's just a consequence of when you bring negatives together, they will repel each other in such a way, right? That's all that's happening here, okay? So does that make sense, kind of what's happening? So the single sentence that we want to say here is a dispersion force is a temporary separation of partial charges, okay? It's a temporary separation of partial charges. As you move these things together, the squishiness comes into play, and electrons move from one side to the other, creating those temporary partial charges. Because as soon as we move those iodines away from each other, what happens? Things kind of go back to the way they were, right? You guys with me on this one?
Aren't they sharing some level of polar bond here though? Albeit a weak one?
Yeah. Well, that's where the energy comes from, right? There is a measure of that attractive energy there.
So what's gonna split them apart?
I don't know, differences in their religion? So the question that was asked is why would they want to move apart to begin with, right? Well, remember, so there is a certain energy that's good when things come together, right? But there also is ambient energy in whatever system we're looking at, right? So even if we get to, let's say, you know, the coldest that we can imagine, that's still quite a bit of energy, you know, the coldest we can imagine on planet Earth, right? That's still pretty darn cold. And that is a lot of energy, and that overcomes the good energy of it coming together, right? The bigger this attraction is, though, based off the electrons, the more we have to have that energy around to split them apart, right? And so for something like nitrogen, again, it's just a very weak attraction, and there's lots of energy in this room, so it's never going to stay in anything other than a gas, right? So that's kind of the idea behind this. Okay? So a temporary separation of partial charges. That's your dispersion force. Okay?
New question.
Yeah.
Presumably I2 can exist in a gaseous state, it would just require very specific.
Oh, it absolutely. It's very easy to get I2 into a gaseous state.
Okay.
Yeah.
So if you have a whole bunch of isolated I2
Yeah.
and you just cool down the environment, is it going to solidify?
Yes. Yeah, iodine actually is a pretty interesting molecule. It's usually used as an example of sublimation. Sublimation is where you go directly from a solid into a gas.
Cool,
Right.
so it just skips liquid?
Sort of. The idea is, I'll say yes to keep it simple for now, right?
So would a slightly more accurate explanation be the circumstance, the pressure and temperature required to have it in a liquid state is so incredibly difficult?
I wouldn't say that. I'm gonna say there's, at standard conditions, it goes very easily from a solid directly into a gas, though. That's what it is. Well, we'll leave it at that.
Okay.
Right? But sublimation is directly, you skip the liquid state, right? Dry ice is probably the best example of that, though. Right? So
Dry ice is fun.
it is. Anyway, next one to talk about. So the next intermolecular force are dipole-dipole interactions. Okay. Now, otherwise just called dipole interactions, either way you want to think about it. Now, a dipole interaction is when there is a permanent separation of partial charges. A permanent separation of partial charges. Now, how would that exist? Well, let's think of a Lewis structure here of something. Okay. So here, let's do our good old buddy. Our good old buddy acetone. A little bit more complex than some of the Lewis structures we've seen. But it's good practice.
So that's what destroys my nail polish.
No, that is what nail polish is, yeah. Right, or nail polish remover, sorry.
Yeah.
So yeah, sorry, I misunderstood. You're absolutely right. Sorry about that. Right? So there's our buddy acetone. Okay, well, what do we know about acetone? What can you guys tell me based off of the kind of principles we've been learning for the past couple of weeks here?
It's polar.
Okay, what makes you say that?
Because the carbons with the HE ones, my vocabulary is going to be great here.
We'll call those hydrogens, just for
Yeah.
argument's sake.
Yeah, they're going to be pretty balanced. So
What
that
do you mean by balanced?
like the hydrogens. Okay, my brain seriously needs to wake up here.
That's all right.
They're not going to be like particularly negative or electronegative,
Well,
right?
let me back you up here for just a second, right? So what we have to do, or what we're trying to assess, is where are our negatives and positives in our Lewis structure, right? Based off of the principle of electronegativity. Got it? Right? So what Rachel's trying to say
In a spectacular
is that hydrogen and carbon are very, very close in their electronegativity. Like carbon is slightly more electronegative. So what she's trying to say is this end here is mostly non-polar, right? Those bonds in there don't really have a positive or negative end. Okay? Does that make sense? Okay? So let's step away for just a second. What's the geometry though of that carbon?
tetrahedral.
How do you guys know?
4 electron groups.
4 electron groups and 4 atoms, right? So tetrahedral molecular geometry and tetrahedral lone pair geometry. Good. Bond angles of?
109.5.
Perfect. Those are on the ball. Excellent. Okay. So we have some non-polar ends here. What about in the middle here with the carbon lead?
Trigonal planar,
Yes.
I'll get it.
trigonal.
I'll get it. So what about in the middle there with the carbon and the oxygen? Trigonal planar, right? What else?
Kind of bent, is that correct?
Trigonal planar is the molecular and the lone pair geometry.
Yeah, 'cause it's got three. Bent is when you've got a lone pair.
What else do we notice about that central CO part there?
It's got a double bond to oxygen.
It does. Yeah.
It's polar,
It's polar. How do you know?
because it's unequal, Sherry, or it's like.
What's
oxygen-
unequal?
The oxygen is pulling more electrons.
Got it, right? Oxygen is far more electronegative than carbon is, which means that it is winning the tug of war to that carbon. And if it wins the tug of war to that carbon, that oxygen is always going to be feeling partially negative. And that carbon that it's bound to is always going to be feeling partially positive. Right? Remember, that's what we did our assessment with in the last class there, right? Looking for our polar bonds. Is that oxygen ever going to be not partially negative? No. So that's what I mean by a permanent separation of partial charges. This is going to have a permanent dipole, as opposed to dispersion where it was just based off of what's around it. Make sense? Right? Okay, so what do you think is going to happen here? Oh, I'm sorry, yeah, what's up?
Do the lone pairs on the oxygen, does that make it more like negative?
It means overall it would have a dipole in that direction, absolutely.
Okay.
But I'm talking about kind of how the atoms feel, right? You're absolutely correct, right? The lone pairs affect the overall dipole of a molecule. Mhm. So here's something partially negative. Guess what partial negative things are attracted to? Partial positives. Wow, right? So if we have multiple of our acetone molecules here, right? Let me hopefully make this a little bit easier on myself, right? Right? So if we have multiple of our acetone molecules start to interact, what's this oxygen going to be attracted to?
That carbon.
That carbon, right? So they're going to start to make some kind of interaction between those two, right? I probably shouldn't draw that. That looks like electrons, right? Okay. So they have some kind of interaction between those two. Got it? Negatives are attracted to positives. That's all it comes down to. Is that ever going to disappear? No. And so these dipole interactions tend to be stronger than individual dispersion forces. Because dispersion, like as soon as you start to move things away, they disappear, right? These are never going to disappear. What's up?
Is the way then that when they mix two things and change around, is that because of the charge like this?
Ask that question again, I'm sorry.
Like if I have substance A and substance B and I slam them together and I get this new thing, is that because of this charge stuff?
That sounds like a reaction happening.
Yes.
Are they affected by these forces?
Do they,
Yes.
do they happen because of them? Or they're lots of factors?
Yeah. I think the simple answer to your question is no. However, negative things do attack positive things for reactions to happen, right? These two aren't going to react with each other, right? They're just going to interact, right? Now, if you put something different in there that's negative and positive, then a reaction might happen, absolutely, right? So that's what I'm not trying to hedge my words here. I'm just saying it depends on what you're talking about. But at the end of the day, everything in chemistry is basically explained by electrons doing something. Here they're interacting. In your example, they'd be doing a reaction though, where you change where the electrons are, right?
And would one thing prefer another thing with a similar positive and negative, or does it just go to the strongest positive thing?
Yeah, so we have to be careful if we ascribe,
Rules.
well, no, not rules, it's kind of if we anthropomorphize a molecule saying, well, it wants this more than it wants, right? There's no sentience to an acetone molecule, right? If it's gonna find whatever's the most negative or positive and go to it, right? But not everything can fit around one specific molecule, for instance, either, right? So there is some competition to that. Okay?
Yes. Thank
Cool.
you.
So those are what dipoles are. Permanent separation of partial charges. Yeah, what's up?
Is the dipole-dipole interaction like the one that's between inside the molecule, or is it the one?
No, remember we're talking about intermolecular forces. So between the molecules. the blue stuff that I'm drawing in there. The negative of one attracting the positive of the other. Okay? All right, last one, and what everyone always says is the most important, and it sort of is, hydrogen bonding. Now, hydrogen bonding is just a specific type of dipole-dipole interaction, in my humble opinion, right? And I'll tell you what I mean with this. Now, a hydrogen bond, for what we are going to learn in this class, can only happen in 3 cases, okay? Those 3 cases are when you see a molecule that has a hydrogen bound to either a fluorine, an oxygen, or a nitrogen, okay? So when you see a hydrogen atom bound to a fluorine, an oxygen, or a nitrogen, then we're going to start to see hydrogen bonding form.
You said oxygen, fluorine, and nitrogen?
What do you guys know about fluorine, oxygen, and nitrogen?
They're electronegative.
In fact, they're ranked what?
1, 2, 3.
1, 2, and 3. You think that's a coincidence?
I think not.
No, probably not, right? So what's going on here? F bound to H, O bound to an H, N bound to an H. Okay? As you guys told me, fluorine, oxygen, nitrogen are extremely electronegative. So what do we know about these bonds? They're extremely polar, right? Which means we've got a pretty significant separation of negatives and positives, right? So what is this? Well, it's just a dipole, right? All we're talking about is a permanent separation of partial charges. It's just when we're dealing with hydrogen bound to those atoms, then we have to think of hydrogen bonding, okay?
Are there any particular differences in hydrogen bonding other than the fact that it occurs between FO and then, like, are there any other particular characteristics of it that separate it
Absolutely.
from dipole?
Yeah, there's entire textbooks written about hydrogen bonding.
Oh boy.
So I will say yes, but I won't go into that. It's not really important for what we need to know here, but I'll be happy to answer specific questions later on if you want. Okay? My point is this. Yeah, Andy, what's up?
Why are we talking bonding now? Is that really?
It's just the name of it. It's just the name of it. Yeah, I didn't pick these names. They call it hydrogen bonding.
Okay.
So this is considered a very important intermolecular interaction because it kind of makes life possible in many different ways. So that's kind of why it's ascribed this separate importance in the textbook and when you read through and watch videos and all this kind of things. And I'm not trying to downplay it, right? Hydrogen bonding holds our DNA together, right? It's what causes ice to float, otherwise it would sink to the bottom of the ocean when it freezes at the North and the South Pole. And that would cause problems too, right? If you get ice and it sinks, then it's down at the bottom and it freezes and sinks, right? So there's a lot of very, very, very important properties that come out of hydrogen bonding, okay? It's why water has such a high boiling point, right? You got a lot of hydrogen bonding going on in water. You've got a lot of intermolecular forces in water. And to be able to boil something, we have to break all those intermolecular interactions, and then they can go into the gaseous state, okay? That's what we use intermolecular forces for. And that's why the statement is kind of made like dissolves like. So let's think about this for just a second. Let's say you have 2 polar things that you mix together. What would likely happen? Well, if we have 2 polar things, we know that they have negative and positive ends on them, correct? So what happens whenever you put any negative and positive thing together? They're going to interact in some way, right? And so that's why we say like dissolves like. The more similar you are in properties, the more you can make intermolecular forces, And then if you're a solvent, it means you can dissolve that specific compound. That's all it means. Okay? Looking for negatives and positives in some way that they can interact. That's what intermolecular forces are. So know your three intermolecular forces. Make sure you can describe them in some competent way, I guess, for lack of a better term, right? Can you explain them to your friends, maybe, is the other word I'm looking for here, right? When your friends ask, what did you learn in class today? Say, well, let me tell you about squishiness. And you can talk to them about dispersion forces, okay? But they're really, really, really super important. They explain a lot of how things stick together, how things react, why certain products are made and why things can dissolve, why they have a higher boiling point, why they have a higher melting point, all these kind of things. It's all based off of how much are those molecules talking to each other. How strong are their communication skills? Got it?
Got it.
That's what it comes down to. Okay? Cool. So, questions?
Why didn't the life versus life rule actually work out in the lab?
Because it's not that simple, right? Life doesn't just come down to these intermolecular forces. Life does, and at its base level, we can explain it by electrons interacting with something else, right? There are plenty of more intermolecular forces, but every intermolecular force, the ones that we know about, and even the ones that we haven't talked about, all come down to how electrons are finding something positive. Really, that's all it is. Okay? What's up?
So something dissolves without it needing to bond to another thing,
It's a process called solvation. Literally, the solvent surrounds that specific molecule, right? So if you think about, well, I don't know, I don't have the pictures, so otherwise I'd try to show it to you. But sugar, right? So table sugar has a lot of OHs on it.
Yeah.
A lot of hydrogens bound to oxygens, and we know that sugar is very soluble in water. Well, the reason why is because sugar can make a lot of hydrogen bonds with the water, right? So that's a good thing for it to form.
Okay.
A good in the energetic sense, right?
Okay.
So if you want to think about it like that, the more we can match different properties, the more likely it is to be soluble. All right. Okay, let's see. We left on right here. Okay. So this is where we left off in our slide, so we'll go back to that. Or to the next one here. Okay. So now that we know everything there is to know about bonds and how to draw them and where the negatives are and where the positives are and predict polarity and how molecules talk to each other and all this kind of stuff. Okay? Now I'm going to wreck that beautiful picture that you guys have. Okay? I'm going to tell you that it was all mostly a lie. I know, I'm sorry. It's a lie that is extremely good, though, which are always the most dangerous types of lies, right? But if we think about this for a second, so let's say that I wanted you guys to build or draw methane for me, right? So CH4. Okay? And you guys could draw the Lewis structure for it, and I could ask you guys about the molecular geometry for it and all this kind of stuff, right? You tell me it's tetrahedral, and it has 109 to 0.5 degree bond angles and all these kind of things, right? You guys ever asked why it's 109.5? What's up?
Because that is the maximum angle, or it's like the maximum angle where all the bonds are equally apart.
Right, that's to put the maximum space in between things, right? How are bonds made?
Electrons.
Electrons. Where do electrons live?
Orbitals.
In orbitals. Now we got to think back here for just a second. So if we're looking at our buddy carbon here, where are the valence electrons living? Well, the valence electrons are living in the 2s and the 2p orbitals. How many 2p orbitals are there? 3, and they're named px, py, and pz. because they lie on the principal, right, Cartesian axis coordinates. What's the angles in an XYZ axis? They're all what?
90.
90 degrees. So what's the angle between the three orbitals?
90.
So where in the world do we get 109.5 from?
They're in between. The,
Electrons only live in orbitals, how can you get in between?
because there's multiple orbitals packing in into.
Nope, there's only the S and the P's. Right? That's the question I'm asking you. How in the world can we square that circle, so to speak, right? We say, well, our angles are all 90 degrees, but we know with 100% certainty that there are angles outside of that, right? So what we have to talk about is where we came up with this good lie for you guys. Here's the lie. When you guys have been drawing Lewis structures and molecular structures, these are just approximations, right? These are visualizations of what's happening. And they are extremely good, okay? They're extremely good. Otherwise, I wouldn't teach them to you guys, okay? They're accepted by every chemist around the world, except for maybe a couple of nutsos here and there, right? But drawing a Lewis structure is not anything that's incorrect. But it doesn't paint a complete picture of where all the electrons are, and it can't explain to us where the different, or how we get these different angles in our geometries. And so to rectify that, we're going to talk about something called molecular orbital theory, okay? And molecular orbital theory is going to explain to us where do the electrons live in molecules, okay? So if you remember way back, we talked about atomic orbitals. Atomic orbitals being sp, p, and f. Got it? As soon as we mix two atoms together, we no longer have atomic orbitals, now we have molecular orbitals. And so that's where we're going to kind of go with this. We're going to talk about how and where electrons exist in more complex structures, and why we see some of the behavior that we do, okay? And why oxygen doesn't kill us instantly, even though it really should in some ways, okay? So we'll try and answer all those simple questions in the next week or so, all right? But before we get to the fun stuff, we have to do the complex stuff here, okay? So this is kind of what I was talking to you guys about here, right? How do our individual orbitals lead to our shapes? But what I want you guys to start to think about is when we mix our atomic orbitals, they have to overlap with each other for a bond to form. What I mean is this. So when two atoms come together to form a bond, they basically have to have a head-on collision. Their orbitals have to overlap with each other, okay? So what I'm trying to show you guys here is if we have two hydrogen atoms, the only thing we have are s orbitals. Well, a sphere is a perfectly symmetrical shape, right? Is there any way we can smash two spheres together and not have them overlap? The answer is no, right? But if we try to overlap a hydrogen with a 2p orbital, right? Remember, our 2p orbitals have these lobes on either side of them. We have to have this hydrogen come in at a specific angle, at a specific distance to form that bond between the fluorine and the hydrogen, okay? So we have to overlap orbitals in a directional manner. The lobes have to interact with each other. Got it? What's up?
So in that picture, is that like the two atoms like actually overlapping, or is
Oh, yeah.
it just like supposed to represent like kind of like a 3D?
No, they're overlapping.
Okay.
Remember, orbitals are a mathematical function.
Right.
So if, just like any function, I can add them together.
Okay.
And when I add them together, I get something that is a combination of the two, right? X plus X is 2X, right? So that's what we're showing here, okay? All right, so this is kind of, again, just a little bit of a summary here. How do we get the 90 degrees for the tetrahedral, but we only have these orbitals, all this kind of stuff there, right? So that's what we're going to try and solve with this theory that I'll introduce to you guys here. Okay. All right, so here's the tool that we're going to have to use. So to be able to get these other angles and geometries, we're going to have to invoke something called hybridization, okay? Now hybridization is the idea that we can mix atomic orbitals to come up with something that's in between, okay? Now the way that I'll talk about this is by using paint, all right?
Paint?
Yeah.
Soft paint?
No, the paint that exists in our brain, right?
Like mixing colors?
Yep. So let's say that you're bored this weekend and you want to repaint your dorm rooms, right? Because you know what? Screw the security deposit, right? Who cares? What are they gonna do, right? Oh crap, I'm recording again, right? So let's say, that you wanna paint your room purple. So you're all excited about it, you're happy, you're thrilled. You go, you drive to Lowe's, and guess what they're out of?
Purple.
Crap. Don't worry. They've got buckets of what? Red and blue. Problem solved, right? I get 1 gallon of red, and I get 1 gallon of blue, and I mix them together, and I get purple out of it, right? That makes sense. So that's what you do. So if I mix, here's the thought here, right? So if I mix 1 gallon of blue paint with 1 gallon of red paint, what do I get?
2 gallons of purple.
2 gallons of what we'll call purple, but looks a little bit more like pink. It turned me on. I don't know how that. You guys get the idea here? The idea is garbage in, garbage out. What you put in is what you get out. The scientific way of saying this is conservation of energy, right? Everything has to be accounted for. If I have 2 gallons that I put in, I better get 2 gallons out. If I put 2 orbitals in, how many orbitals do I get out? 2. Got it? That's what I'm talking about. So here's how the hybridization idea works. If I mix an s orbital with a p orbital, okay? We're gonna get this very oddly named orbital out of it. It's gonna be called an sp orbital. I know, shocking. But what I will get is 2 sp orbitals. You guys with me on this? Because I mixed 2 gallons of paint, I mixed 2 gallons of paint, I better get 2 gallons of paint out. Got it? So I mix an S and a P, and I get 2 sp orbitals. Good? All right.
When we mix 3 things, do we get a 3-letter orbital?
Yep.
Okay.
We'll get there in just a second. But let's think here for just a second. So stepping away from the discussion of paint. Take carbon for an example. Where are the electrons living in carbon? They're living in an S, and they're living in how many p orbitals? 3. Frickin' mosquito, man. Right? But I only used 1 of my p orbitals to make my hybrids. So what did I do with my other 2 p orbitals? Nothing, right? They are unhybridized p orbitals. So I still have my other 2 p orbitals here. You guys with me on this? So when we hybridize orbitals, when we start to think about this, remember, we're always going to be dealing with an s orbital and my 3 p orbitals.
What about when you mix in G's?
We'll get to there, right? You guys following along with this though? Right?
Wait, so shouldn't there be 2 P's on the left side too?
Sure. There should be 3 of them over here, right? Well, if we just mix 1 S and 1 P, we get 2 hybrid and 2 unhybridized. Good? Now guess what? I'm going to make another shocking statement. Electrons that live in hybridized orbitals behave differently than those that don't live in hybridized orbitals. Wow. Okay? And that's going to be important. Unhybridized orbitals are going to tell us how many, what we'll call pi bonds form. Pi bonds are double bonds and triple bonds. Okay? Well, we'll talk about that in just a little bit too. let's expand this idea here just a little bit. So let's say we're gonna go paint our room again, okay? But now, we mix 1 gallon of blue and 2 gallons of red.
You're gonna
Okay.
get a really reddish purple.
Exactly, right? We're still gonna get a purple, but it's gonna have more of the red characteristics to it. Do you guys catch what I mean with this? If you take the stupid color, well, not stupid, the fantastic color analogy out, right? We're getting a mix of the two, but it has more characteristics of one of the colors. Do you think that's gonna change how things react?
Yes.
Yes. Okay. How many gallons of orbitals are we gonna get out though? 3. Got it?
What decides how many of the p orbitals the s orbital joins to?
I do. At the moment. Well, I'll tell you how we can figure it out though, okay? So for the moment, just kind of follow along with the analogy, okay? So now I've mixed 1 s and 2 p's. How many unhybridized orbitals do I have?
1.
Just 1, right? I still have my one of my p orbitals available. Yes?
So how do you miss another SP orbital? Like, I thought there were only 2 different S orbitals. Like, how do you have a third one now?
We have 3 orbitals in, 3 orbitals have to come out.
Okay.
So kind of, if you think a little bit about with this, the idea that we're still making purple, but it's more red, right? We don't have as much characteristic of our blue in there anymore. We don't have as much characteristic as the S,
Okay.
right? But we still only have 1 to mix in.
So it's not like an entire orbital is in the SP. It's like parts of them.
No. We mix these entire 3 orbitals in here,
Yeah.
right?
Okay.
But we just have 1 that isn't mixed, our unhybridized. What's up?
Well, for the electron configuration of like the second row anyways, doesn't it have 3 available SPs anyways?
It only has
4.
Those are atomic orbitals.
Oh. Okay.
Okay. And I think, can you guys figure out what I'm about to do next though? Now I take 1 of my S and all 3 of my P's, right? Oh, I'm sorry, I forgot, let me back up for you just a second. So, I forgot to give you guys a name. So when we mix an S and 2 P's, we make 3 sp2
2?
orbitals, okay? Which makes sense, right? We mix an S and 2 P's and we get sp2 orbitals, got it? That's all it comes down to.
So when you add another P, it's gonna be SP3.
You got it.
Sweet.
So now we add our 3rd gallon of paint. We get 4 gallons of, there it is. We get 4 gallons of sp3 orbitals out of it.
So is the exponent like,
It just tells us how many orbitals we've mixed in there.
so in our case, it'd be telling us how red the P is?
Yep.
Okay.
Yep. Good? That's all I'm gonna, this is everything I'm gonna tell you guys about. Now I just have to make it look scientific and really confuse you guys about it. You ready?
Yeah.
But this is, so if you guys keep this in mind, this is what we're gonna be doing. And the point of this, the really important point is that we get purple every time, but that becomes more red. So we change our characteristics. And SP is gonna behave differently than SP2. It's gonna behave differently than SP3. All right? And we have unhybridized orbitals. Except we don't have unhybridized orbitals here. That's also gonna be important. How do we know we don't have unhybridized orbitals here? Well, how many p orbitals do I ever have? 3. And they're all being used to hybridize things. You guys got it?
Mhm.
You guys catch those important ideas there? Yes? Okay. So now we're going to take those paint bucket ideas and visualize them as orbitals. All right? That's what the next couple of slides are all about. Here's my blue, right? Here's my red bucket number 1. When I mix my blue and my red, I get my purple bucket here, right? That's what I'm showing at the top. That's what an SP set of orbitals look like, right? I form 2 SP orbitals, and they kind of look like a mix of the 2 colors, a mix of the 2 orbitals ahead of them, all right? They have characteristics of S, they have characteristics of P. Okay? My other 2 orbitals remain unused, and we'll say where they are used once we kind of finish this part up. Good? Okay. Let me go ahead and kind of jump to the conclusion here a little bit. Our orbitals are used to interact with things. They're used to make bonds. How many how many hybrid orbitals do we have here?
2.
2. How many bonds can we make? 2. What are the angles in between those 2 orbitals? 180. What geometry has 180 degree angles in it that has 2 things around it?
Linear.
Linear. You guys starting to see where this is coming together? Okay, each of these hybridizations corresponds to a specific electron pair geometry. Okay, anything that has a linear electron pair geometry is sp hybridized. Got it? If I take this and I visualize it in a different way, so still the paint buckets, here's my blue paint, okay? Here's my red paint buckets. If I mix these 2 together, here's my purple, and there are my 2 reds that are unhybridized. This is the way that you guys will start to see this in the book, and if you guys take a look at that sheet of equations that I give you guys on exams, this is what's seen at the end of that sheet there, okay? Each of these boxes represents an orbital, and the arrows represent the electrons that are in there. That's all it comes down to. Okay? So, something happens, and magically we get an electron up there. Nobody asks too many questions. And because of that, we can magically hybridize an orbital. Okay? So, here's what this scientifically comes down to. Magic, a little bit more magic, purple paint. Got it? All right? So that's what this is going to come down to. I don't need you guys to know about the whole promotion thing. I don't need you guys to know exactly how this happens yet. All right? So we'll finish this up then on Monday. There should be a quiz opening up for you guys today. I think at noon. Right, and it's due tomorrow sometime, I forget exactly off the top of my head, right? But keep an eye out for that. Everything on the quiz is about you guys drawing structures. So the last question is for you guys to upload your pictures of that stuff, okay? That's up. Hold on a second.
Is this stuff going to be on the exam?
This, yes. Yeah.
Are you gonna turn it into?
Yes. Because all the p orbitals are degenerate. They're all the p orbitals. You can't just have one without the other. We just occupy. Right? That's the
Yeah, I
difference.
got up at 7:45.
Okay.
I cleaned my room a little bit. I made my bed. I found my clothes. Well, I found some clothes. I didn't find